Here's the brain teaser in question. What we're looking at here is a circuit diagram of a battery and a switch connected to a pair of wires that are each 300,000 kilometers long. And those wires loop back to a light bulb that is placed 1 meter away from that battery and switch. And the question is, when that switch closes, how long does it take for a signal to be intercepted by that light bulb? How long does it take that light bulb to light up? Or how long does it take a signal to propagate from the source to the receiver? There's lots of great discussions, lots of great videos that show many different ways of thinking about that problem, but the time is the gap divided by the speed of light. So the time that it takes for any current to be picked up here is going to be 3 nanoseconds. Now we'll address the same problem, but we're going to do it on not quite such a large system. We'll do it on something just a little bit smaller. So here's an image of the solid model that we're going to create. It's going to be composed of a 10-volt source and a 50-ohm receiver or sensor. And we'll consider wires that are just 30 meters long. And again, the gap here is going to be 1 meter. So this is the structure that we're going to simulate. But before we do that, there's something to point out here. What we're dealing with here, this system actually has symmetry to it. So we could actually exploit that symmetry. We could say, okay, the fields around that plane that we see there, the fields are going to be symmetric, and they're also going to be symmetric about this plane. Both of these, you should be able to see by examination that what we have here are 2 planes of symmetry in the system. So let's jump into the software, where we already have the geometry partially built up here. We have a couple of domains representing the source, the battery and the switch, and the sensor, the light bulb. And then we have all the other domains as well. And then we have a set of other geometry primitives here. And what we'll do is we build all those up together to represent the space around. And then we're going to cut that all in half such that we have our 1/4 symmetry model of the entire structure that we're going to work with. So what we're looking at right here, this is the volume around the wires where we're going to be modeling the electromagnetic fields. And the wires, source, and the sensor, those are all going to be modeled just as surfaces. So these boundaries right here are going to represent the outsides of the wire and the source and the sensor. So with that geometry built up, we can assign a material property, and we'll assign the property of perfect vacuum. And that's going to set the permeability and permittivity to 1 and the conductivity to 0. Now we will define the physics involved, and we'll use the transient electromagnetic wave formulation, because that's going to capture all of the phenomena that we want to model here. We'll add the perfect magnetic conductor condition on these 2 boundaries here, representing the boundaries parallel to one of the symmetry planes. And we can also add a perfect electric conductor boundary condition on this other plane representing the other plane of symmetry. We'll add a lumped port boundary condition to these 2 boundaries right here representing the source. And we'll change the voltage to 10 volts. So this is going to be the voltage signal that's applied starting from the initial values. The initial values are 0 everywhere, meaning that the fields are going to be 0 at time equals 0, and then we will instantaneously flick that switch and apply a potential of 10 volts across this gap defined by the lumped port. We'll also, at the receiver side, add a lumped element, and that has a default resistance of 50 ohms, and we'll leave that as it is. We'll add a scattering boundary condition around the outside boundaries here, and this scattering boundary condition will represent a boundary to surrounding free space. So any signal that's going to radiate away from our structure, away from our source and wires and receiver, is going to radiate through this boundary unimpeded. So it's as if that boundary wasn't there, it's just transparent to outgoing radiation. All of these boundary conditions that we've added have been overriding this default boundary condition of perfect electric conductor. So that perfect electric conductor condition is left on all of the boundaries representing the superconductive wires, and that is reasonable to do. The default domain condition that we have here, this simply sets the material properties to be coming from this material property branch. So with that, we've completely set up the physics, and let's take a quick look at the mesh. We can change the mesh size to be coarser, or in this case, we'll set it just to be a little bit more refined than the default. We'll talk a lot more about these mesh settings a little bit later on. We'll now get ready to solve the model. And for that, we're going to add a time-dependent study. And we're going to solve from 0 to 3 microseconds. And we'll change the tolerance here from this default value to a tighter value of 5e minus 5. We'll talk more about that tolerance, as well as how that interplays with the mesh a little bit later on. And before we go ahead and solve this, I'm going to come to the output settings. And rather than just saving the outputs at 0 and 3 microseconds, we'll store all of the steps taken by the solver. So with that, we're ready to go ahead and compute the solution. And with these settings, it's going to take a couple of minutes to solve. And here's our model after solving. And what we'll do here is we'll just move things around a little bit so that we can really zoom in on the part that matters here. So we have a few visualizations already set up so that we can go ahead and go through them. And what we'll do here is we'll start to march this forward in time. So this visualization here shows us the pointing vector as the black arrows, and these are scaled logarithmically. And then on the surfaces, you're going to see the colored arrows are going to be the currents flowing along the wires. So we'll march that forward a few more nanoseconds in time. And we can see that as that current starts to flow, you start to have a signal radiating out through space. And the explanation for that, anytime you start to get a change in the electric field, you're going to start to get a signal radiating out through space. And as we march that forward, we see the signal gets from the source, radiates from the source to the receiver, and we'll start to get significant currents on the wires around the sensor. And now we start to see those are starting to show up there. Again, these arrows are also logarithmically scaled. So we can go ahead and march that forward a little bit more in time. And what we see here is those signals look a little bit noisy. You know, it looks a little bit jagged there. And we'll talk a little bit more about that. And we definitely also see some signal radiating away here into the into surrounding space. Now, as we keep going forward, we can see that signal, that the power flow is power is being guided by these wires along these two parallel wires. So it's kind of a parallel wire transmission line. And let's go ahead and march forward here. We'll just go forward here a little bit further in time and zoom out. And now we see, let's kind of zoom in on just one of these ends here. So again, we see the current flowing along this one wire. We see that current is inducing a back current here along the other wire. And that's all going on, you know, before there's any signal, before there's actually any information going across this bend here. So it's really the fields out here in this region, they're still 0. But now let's go ahead and just go forward just a step forward here a little bit more. And what we're going to start to see here is the currents on those wires as they start to go around and how the power is being guided around that bend there. And what's particularly noticeable here in this kind of visualization is that we're starting to see also that the fields are actually getting a little bit radiated away here. It might not be completely obvious, but if we're looking at these fields right here, you can see that there's actually some radiation away from this tip here. So there's some signal radiating off of these two ends as that signal propagates around that bend. And if we keep going here, now we're starting to see kind of what I think a lot of people initially expect, that solution, that as you turn that current on, the current's going to propagate along that wire. And let's go ahead and just march a little bit further forward in time. And now we're starting to see, let's go ahead and take another look at this, a little bit more of a symmetric look, and just keep marching forward. And again, we see that current flowing in and out of the source. And we see that there is current flowing through the receiver And now we're seeing at 100 nanoseconds that signal, that main signal, is then starting to get intercepted by that receiver. And we can just go ahead and keep going there just a little bit more and see what happens. And we'll take another look at that, at another kind of visualization of this in just a few minutes here. But before we do that, let's also take a look at this plot, which is a plot of the current through the sensor itself. And we'll change the units around here from seconds to nanoseconds, just so this is a little bit easier to look at. And we'll start by zooming in just at the very, very beginning here, the first few nanoseconds. And what we start to see actually is that signal starts to have kind of a smooth rise time centered a little bit around 3 nanoseconds. And we should actually ask ourselves right off the bat, why is that happening? Well, recall that our lumped port excitation, that specified an instantaneous change in voltage across that source. But we're trying to model an instantaneous change on the in the electric fields with a finite-sized mesh and a finite tolerance. Remember our tolerance here, we had set that to 5e minus 5, and we had this mesh right here. Now this mesh is discretizing the wave-like fields. And very roughly speaking, if you're familiar with the Nyquist criteria, you need to have, at a bare minimum, 2 elements per wavelength. So if we wanted to actually capture all of the infinite frequency content that actually exists in such an instantaneous change in the fields, we'd actually need to have both an infinitely fine mesh and an exceptionally fine tolerance here. Obviously, we can't do that. So we have to accept that there's some numerical smoothing or numerical dispersion being added back in around that step change in the applied voltage across our source. Now, keep in mind that in reality, we cannot actually apply a step change in the voltage. Any kind of real switch is going to have some kind of smoothing to it. And in a sense, here our numerical model is reflecting that. So let's go ahead also and zoom out a little bit here and look at the first few tens of nanoseconds. And what we see here, again, is what looks like quite a noisy signal here initially. And again, this is due to the fact that our mesh could have been made finer, and the finer that we make our mesh, the more high frequency content that will resolve, and the tighter that we make the tolerance, the smoother this curve is going to be. Let's go ahead and zoom out a little bit more. And then we see that just at about 100 nanoseconds, we can start to see that second big rise where we saw that signal is propagating all the way along the length of the wires and coming back. And now we see our second plateau and our third plateau and more. And what we can particularly observe here is that from one plateau to the next, all of these sharp peaks, they're starting to get smoothed out and widened. And this is due to the loss in the dispersion in the model, and that has to do both due to the receiver itself and due to radiation away from the system. There is also signal getting radiated away. And if we zoom all the way out, we can see how that evolves over time. These peaks start to dampen out and spread out a little bit in time. And if we look at the shape of this overall curve, we see that that's gradually going to approach a current of 0.2 amps. And recall that we had a 50 ohm lumped element and we had a 10 volt source. So we should expect this to approach 0.2 amps in the limit as time gets very, very large. And this overall shape of the curve that we have here, well, what does that look like? Well, that actually looks like the RL response of a coil charging up. And that's actually exactly what we have here. If we take another look at this, if we look at this system, what we have here is a large inductive loop. So what we're looking at here, the overall shape of this curve, is that inductor getting charged up. The small signal that we have at the very beginning here, that is due to the electromagnetic waves propagating and bouncing back and forth between those wires at the very beginning of our start time. Then we're start to seeing this signal as the signal bounces around the ends and comes back and forth. And these ripples that get damped out over time, those ripples actually can tell us something about the shape of the bend. If we were to design that bend a little bit differently, we'd get a little bit different sized ripples. And the damping out of those ripples over time, that's due to the various sources of loss here, both the receiver and radiation away from the system. So this plot gives us a whole different perspective on the system as a whole. There's one more animation we'll look at, and this is a little bit different. This animation shows, with transparency, it shows a plot of the energy density in space. So this is a little bit different from all of the other visualizations that we've looked at up until now. What we're looking at here is where the energy is being stored within this system. This energy density is a scalar field rather than a vector field, rather than everything else that we've been looking at so far. This just has a single value at each point in space, rather than a value and a direction. So this gives us a little bit of a different way of thinking about the system. And again, what we can see here initially is we can see that high frequency content propagating down and reflecting around the two wires. And we can see that those waves are starting to damp out over time. And then as this progresses forward in time, we can see that there's more and more energy being stored in the system. And again, since that's log scale, it's growing actually quite gradually. We'll look at it one more time. There you see that high frequency content, and you see lots of radiation away, especially from the tips at the ends. And then you see that primary signal, that first big pulse coming in, and then you see the further reflections as that energy builds up in the system over time, and you see the wave-like nature of this. And with that animation, we're going to go ahead and finish up.